lecture series on differential equations for undergraduate students. Today's lecture is in continuation of the Strum Liouville boundary value problems. In this lecture, we will discuss the properties of Strum Liouville boundary value problems. For properties, let us for convenience define a linear differential operator as Ly is equal to minus Pxy dash whole derivative minus Qx into y. Here this L is actually an operator which is when operated on the function y gives me the derivative of Px y dash with minus sign minus Qx times y. Now, we can rewrite the Strum Liouville differential equation Px y dash whole derivative plus Qx lambda Rx y is equal to 0 in the terms of this linear differential operator as Ly is equal to lambda Rx times y. Now, let us assume that these coefficients Px, Qx, Rx they are all continuous as well as P dash x is also continuous on the whole interval a b on which this differential equation is being defined. Moreover, we would be assuming that the Px and Rx to be positive on the whole interval, that is for all x belonging to a and b. Then an important property of the Strum Liouville problem is known as Lagrange's identity. Let us first find it out that how we are obtaining it and what it is. Let u and v be two functions on interval a b having continuous second derivatives on the whole interval a b. Then we can write this integral L u into v integrated over x for the whole interval a b. Now, since L u is that is L is an operator which is operated on v. So, just by the definition of that operator we can write it as integral a to b minus p u dash whole dash minus q u v dx. Now, rewrite it as minus p u dash its whole derivative v minus q u v dx. Now, separating both the integrals we get minus a to b the derivative of p u dash into v integrated with respect to x minus integral of q u v with respect to x on the limits a to b. Now, if I integrate this first integral by part, we do get p u dash, because I have taken this p u dash and its whole derivative as the integrable function, and into v evaluated from a to b plus integral a to b p u dash v dash dx, and the second integral is as such integral q u v dx from with respect to x on a to b. Now, the first integral here again we are going to do by with the integral with parts and the taking first function as u dash. So, what we will get the first thing as such p u dash v from evaluated from a to b plus p u v dash evaluated a to b minus integral u p v dash and its whole derivative integrated with respect to x on a to b minus the last integral as such q v with respect to x on the interval a to b. Now, again what we are getting is making this rewriting the first two lines p u dash v and p u v dash we can write p as common and we are getting it as u dash v minus u v dash evaluated from a to b plus this integral we are writing as one integral again. So, what we would get the derivative of p v dash with minus sign minus q v and u has been taken common integrated with respect to x on the interval a to b. Now, you see this is what we are getting is as the operator L operated on the function v. Let us write it in this next line. So, what we are getting is we have started with the integral L u v with respect to x on the interval a to b and we are getting it as minus p x u dash v minus u v evaluated from a to b plus a to b L of v u integrated with respect to x. This says if I am taking this both operator one and integrals on the one side, this simply says is integral a to b luv minus lvu dx is same as minus px u dash vx minus ux v dash x evaluated from a to b. Now, this in general is also known as Green's identity, and this we are evaluating on the general interval a to b. Now, we are talking about the properties of Sturm Liouville problem. So, not only Sturm Liouville differential equation, but also the boundary conditions. So, we have assumed that u and v are such that they are being operated on this Sturm Liouville or this linear operator. Now, let us assume that they are satisfying the boundary value conditions of Sturm Liouville problem. So, what we do say that says is a1 u a plus a2 u dash a should be 0, b1 u b plus b2 u dash b should be 0, and similarly for v a1 v a plus a2 v dash a should be 0, and b1 v b plus b2 v dash b should be 0. Now, here we will assume that at least actually one of these a1 a2 b1 b2 must not be 0. So, we are assuming that a2 is not 0 and b2 is not 0. That says is we can write u dash u and v dash in the terms of u and v. Let us see how. U dash a from the first equation can be written as minus a1 upon a2 u a, and u dash b as minus b1 upon b2 u b. Similarly, v dash a as minus a1 upon a2 v a, and v dash b as minus b1 upon b2 v b. Now, let us come back to our Green's property, which says is that integral a to b luv minus lvu dx is minus px u dash x vx minus ux v dash x a to b. Now, the right hand side we are just putting the values, that is evaluation. So, it would be minus pb u dash b v b minus u b v dash b plus p a u dash a v a minus u a v dash a. Now, for u dash v dash at a and at b both places, we will replace by the just now we had used that boundary conditions, and from there the values that in the terms of u and v. So, we can write as minus b 1 upon b 2 u b v b plus b 1 upon b 2 u b v b with multiplication as minus p b, and the second term also p a minus a 1 upon a 2 u a v a plus a 1 upon a 2 u a v a. Now, we see the terms in the bracket, both the terms in the bracket here, this is 0 as well as this is 0. This says is this whole right hand side will come out to be 0. Now, what we have got, thus we summarize, the Lagrange's identity says if u and v are two functions defined on the interval a to b having continuous second derivatives on the same interval a to b, then integral of luv minus lvu with respect to x on the whole interval a to b would be equal to 0 when in the boundary condition a2 and b2 are not 0. So, we are talking about Sturm Liouville boundary value problem, that is the differential equation as well as the boundary conditions, and in the boundary condition we are assuming that when a2 and b2 is not 0. This thing we can also say in the terms of inner products. What are inner products? Inner products we are defining as inner product u and v is defined as integral of u v bar with respect to x on the interval a to b. You see here in this one we are having this v bar is, we are assuming that u and v actually the complex functions and v bar is nothing but the complex conjugate. So, of course, when u and v are not complex, they are real, v bar would be same as v, but notion of the inner product is defined in the terms of complex functions. Now, let us rewrite this Lagrange's identity in the terms of this inner product. Then what we are saying is inner product of lu comma v is same as inner product of u comma LV. That is, we can interchange this operator L, and this is what Lagrange's identity is saying. Let us see the implication of this Lagrange's identity on our Sturm Liouville boundary value problems. So, implication of Lagrange's identity, the first implication is that reality of eigenvalues. What it is? See, this is defined here as theorem. All the eigenvalues of Sturm Liouville problem Ly is equal to lambda r y with boundary conditions a1 y a plus a2 y dash a is equal to 0, b1 y b plus b2 y dash b is equal to 0 are real. So, how to show it? We would be showing it using the Lagrange's identity. See the proof. Let lambda is a complex eigenvalue with eigenfunction phi x. Here what we are assuming? We are starting with that lambda and phi both are complex. That says is let lambda is of the form mu plus I nu. Now, what we would show? We would show using the Lagrange's identity that this mu term, that is mu is 0. So, that we get lambda is equal to mu, that is only a real one. Since we had assumed that lambda and phi to be complex, so phi also we are assuming of the form u plus I v x. Now, with mu, nu, u and v all we are assuming is real. Now, applying this Lagrange's identity on u and v, that in Lagrange's identity we are having inner product of Lu comma v is same as inner product of v comma Lu. There u and v, if I assume same as phi, then what we would get? We get that inner product of L phi comma phi is same as inner product of phi comma L phi. Let us expand it. This says is integral a to b L phi phi bar dx should be same as integral a to b phi L bar phi dx, where bar is denoting the complex conjugate. Now, since this phi is eigenfunction for lambda, so L phi would be lambda r phi, and L. So, let us substitute it in this identity. What we get? Lambda r phi phi bar dx is equal to integral a to b phi lambda bar r bar phi bar dx, because L phi is lambda r phi, its complex conjugate would get lambda bar r bar and phi bar. Now, we are knowing is that in Sturm Liouville problem r is real function. So, r bar would be same as r. Thus, rewriting this and taking both the things on the one side, we would get lambda minus lambda bar integral a to b r times phi dot phi bar dx is equal to 0. Now, phi we had assumed of the form of u plus I v. So, phi bar would be u minus I v. If you multiply both them, I will get it as r times u square plus v square dx in the integral part, and lambda minus lambda bar, what it would be? Lambda we had assumed as mu plus I nu. So, lambda bar would be mu minus I nu. When we are taking the subtraction, we would be getting as minus 2 I nu, and that we would be plus, and that 2 part we have taken as the 0 side. So, we would be getting this one. Now, you see here u and v were real function, and r we had already assumed that it is a positive on the whole interval a to b. So, what we are having? R is positive, u square is positive and v square is positive. We are integrating a positive function on a interval a to b, finite interval. Of course, this integral can't be 0. So, what would be 0 in this identity? That mu should be 0. If mu is 0, my lambda would be mu plus 0, that is mu only, that is lambda is real. So, we had got using this Lagrange's identity that my eigenvalue of Sturm Liouville problems are real. This is the first property. The second property is again related with this eigenvalues and eigenfunction, that requires one more definition. That property is belonging to orthogonality. Let us first see the definition, what we call orthogonality. Functions y1, y2, yn would be defined, which are defined on some interval a to b, are called orthogonal on a to b with respect to a weight function r x. That weight function has to be positive if the integral r x y n y m bar x dx on A to B is 0 for all m not equal to n. That is, whenever we do have two different y m and y n, then y m into y m bar multiplied with r x, this if I integrate over the whole range A to B, it should give me 0. Then we are calling that the function y n and y m are orthogonal with respect to r on the interval A to B. Also we are defining one more term here, that is called the norm of the function y m. This we are denoting by this notation y m. This is defined as r x y square y m square integrated with respect to x on the whole interval A to B and its square root. So, this term is defined as the norm of y m. One more from here, if we take that norm of phi m is to be 1, then we say the functions are called orthonormal on A B. If they are orthogonal on A B, again we are talking with respect to x and all have norm 1. So, if they are having norm 1, we are calling the functions to be normal, and if they are normal and orthogonal, we are calling them to be orthonormal. Now, if r x, that is the weight function, is 1 uniformly all over there, then what we say is that we are not saying orthogonal with respect to or orthonormal with respect to, we simply say orthogonal, and the definition is also revised. So, see the revised definition. The functions y 1 y 2 are orthogonal on some interval a b if integral y m x y n bar x dx, that is with respect to x on the a b, is 0 for m not equal to n, and the norm now is being redefined as integral y m square with respect to x on a to b and its whole square root. So, we have taken r to be 1, and here we are not using that with respect to r x as 1, that term we are deleting. So, now before moving to the properties of Sturm Liouville problem, let us first do one example to understand this orthogonality. The functions sin m x for m as integer 1, 2 and so on form an orthogonal set on the interval minus pi to plus pi. You see, that says is that we have to show that this y m x for m is equal to 1, 2, 3 and so on is orthogonal. So, integral minus pi to pi sin m x sin n x with respect to x. Now, we do know sin m x sin n x we can write as half cos m minus n x minus half cos m plus n x. So, we are substituting it and putting this in the integral and breaking it into two integrals. Now, integrating both the integrals from minus pi to plus pi, we do get it that half sin m minus n x dx upon m minus n evaluated from minus pi to plus pi minus sin m plus n x upon m plus n minus pi to plus pi again evaluated. Now, we see that m and n both are integers. So, this what we would be getting is that sin x with a multiple integer multiple, here also sin x with an multiple as an integer, and we do know that sin n pi plus or minus is always 0, that we are getting is that this integral is 0. So, we have been through that sin m x sin n x, its integral from minus pi to plus pi dx is 0. So, they are orthogonal, and of course, we are taking that m and n are not equal. The norm, moreover, we can find it out. We see the norm of this function y m x, that is minus pi to plus pi sin square m dx. If you evaluate with the simple ones, we do get is equal to pi. So, the norm of this y m, that is sin m x, is square root pi. Now, let us come to the property of Sturm Liouville boundary value problem. It says is orthogonality of eigenfunctions. What is this property? Again we are writing in the terms of theorem. Let phi 1 and phi 2 are two eigenfunctions of Sturm Liouville problem, p x y dash whole derivative plus q x plus lambda r x y is equal to 0 with boundary conditions a 1 y at a plus a 2 y dash at a is equal to 0, b1 y at b plus b2 y dash at b is equal to 0 with respect corresponding to the eigenvalues lambda 1 and lambda 2 respectively. That is phi 1 is eigenfunction for lambda 1 and phi 2 is eigenfunction for lambda 2, and if lambda 1 and lambda 2 are not same, then phi 1 and phi 2 are orthogonal, or in other words a to b with respect to r x. This r x is the same which is coming in the Sturm Liouville differential equation, that is integral a to b r x phi 1 x phi 2 x dx would be 0 whenever lambda 1 is not equal to lambda 2 and phi 1 and phi 2 are corresponding eigenfunctions. Proof of this theorem, let us see. Again we would be using this Lagrange's identity. You see, we are being given that lambda 1 and lambda 2 are eigenvalues and phi 1 and phi 2 are eigenfunctions, that is L phi 1 is equal to lambda 1 r phi 1 and L phi 2 is equal to lambda 2 r phi 2, that is lambda 1 phi 1 lambda 2 phi 2 will satisfy our Sturm Liouville equation. Now again we are going to use the Lagrange's identity. What we will use in Lagrange's identity, the two functions u and v, now we will take them as phi 1 and phi 2. Then Lagrange's identity says that inner product of L phi 1 with phi 2 is same as inner product of phi 1 L phi 2. Now substitute this L phi 1 as lambda 1 r phi 1 and L phi 2 as lambda 2 r phi 2, we are getting lambda 1 r phi 1 phi 2 dx is equal to phi 1 lambda 2 r phi 2 dx. Now rewriting this, we get lambda 1 minus lambda 2 times integral r phi 1 phi 2 dx is equal to 0. Now we are knowing is that we have taken lambda 1 and lambda 2 distinct, that is lambda 1 minus lambda 2 is not 0. That says is that integral r phi 1 phi 2 with respect to x on the integral on the interval a to b would be 0, that says phi 1 and phi 2 are orthogonal. So they are orthogonal with respect to r x. Now let us see one more property, or rather the use of this property you had already seen, that Legendre equation you had already done in the example. This is actually a Sturm Liouville differential equation. Now if we use the boundary conditions on 0 and 1, you had known that the solution of this equation, one solution you had denoted it by as p n x and you called it Legendre polynomials. You had already proved that Legendre polynomials are orthogonal on the interval 0 1. Here what I am not going to prove it here, I am just telling you that you can see that because it is a Sturm Liouville differential equation using suitable boundary conditions, because you are given there the initial values, you can show that this property can be found out from here also. Similarly, you can, so this is what you had already proved, 0 to 1 integral p n p m dx is 0 whenever n is not equal to m. Moreover, you had already done that is Bessel's equation is also a special form of the Sturm Liouville equation, and its solution you called the Bessel functions. You had already proved that the Bessel's functions are orthogonal. Again you can show them using this Lagrange's identity. Now let us come to one more property. The eigenvalues of the Sturm Liouville problem p x y dash its derivative plus q x y lambda r x y is equal to 0 with boundary conditions as a 1 y a plus a 2 y dash a is 0 and b 1 y b plus b 2 y dash b is equal to 0, and certainly all of a 1 a 2 and b 1 b 2 should not be 0. They are simple, that is to each eigenvalue there corresponds only one linearly independent eigenfunction. Further, eigenvalues form an infinite sequence and can be ordered according to the increasing magnitude, so that we can write as lambda 1 is less than lambda 2 is less than lambda 3 and so on. Moreover, as n is increasing, lambda n is also increasing infinitely. Let us see what this theorem is saying. This theorem is saying that for Sturm Liouville problem, its all eigenvalues are simple. You had understood the terms that simple you have got in the terms of roots and the corresponding solutions. So, multiple roots means is you are able to get two linearly independent solutions. So, here what they are saying is all eigenvalues are simple, that is with respect to every eigenvalue you will get only one linearly independent eigenfunction. And moreover, one more thing we are saying that there are infinite many eigenvalues for Sturm Liouville problem and they can be ordered in the increasing magnitude. That is, we can rename, that is the smallest as lambda 1, then the lambda 2 and so on, and they can increase till infinite. The proof of this theorem we are not going to do because it requires little bit mathematics, which is beyond the course of this particular one. We would see that is, so what we have learned the properties of Sturm Liouville problem. Let me summarize it again. We had learned that is for Sturm Liouville problem, the problem I am writing again on the interval a b with the boundary conditions at a and at b. First property we have done is reality, that all the eigenvalues of Sturm Liouville problem are real. Second property we had learned about orthogonality, that if phi 1 and phi 2 are two eigenfunctions corresponding to the distinct eigenvalues, then they are orthogonal with respect to r. The r is the function which we are getting in this Sturm Liouville equation. The third property just now we have done, that is called the simplicity. The eigenvalues of the Sturm Liouville problem are simple, that is each eigenvalue there corresponds only one linearly independent eigenfunction, and this eigenvalues form an infinite sequence and can be ordered in increasing magnitude as this one. Moreover, as n approaches to infinity, lambda n also approaches to infinity, that says they can go as large as possible. Because we are saying here, so we have said here that is all eigenvalues are simple and corresponds only one linearly independent solution, but we have seen in our previous examples that we are getting this linearly independent solution, that we can always write general solution as c times that solution. So, this c, that is multiplicative constant, we are talking about little bit that one. So, associated with each eigenvalue lambda n, there is corresponding eigenfunction phi n determined up to a multiplicative constant. It is often convenient to choose this constant such that it satisfies the condition of normality, that is its norm is 1. So, that multiplicative constant many times we are choosing a particular value, that is we are not talking about general solution, we have to talk about that particular solution, and for that the constant we choose such that the function becomes normal, because we already know that for distinct eigenvalues the eigenfunctions are orthogonal. So, we come as orthonormal set. So, normality means simply a to b r x phi n square x dx should be 1. Let us try one of our examples. So, what we are saying is that we just want them to form an orthonormal set. So, let us repeat our examples which we have done in the boundary value problem and Sturm Liouville problem and see that is how we are obtaining them. Determine the normalized eigenfunctions of the boundary value problem y double dash plus lambda y is equal to 0, y at 0 is 0 and y at 1 is 0. You remember that this example we have already done and we had already shown that here this can be written as y dash and its derivative plus lambda y is equal to 0. So, we can write it as with p as 1 and q as 0 and lambda as the eigenvalue and r as 1. So, this is again a Sturm Liouville problem. We want normalized eigenfunctions. Again we will just try to solve it the complete here because we had done it in the last lecture. So, the differential equation given is y double dash plus lambda y is equal to 0. The characteristic equation would be m square plus lambda is equal to 0, giving me the characteristic roots as plus minus I root lambda. So, the general solution would be C1 cos root lambda x plus C2 sin root lambda x. Now, satisfying the boundary conditions would give me At 0 C1 is 0, at 1 C2 sine root lambda is 0 because C1 is already 0. So, for C2 to be non-zero, so that we get non-trivial solution, we require sine root lambda should be 0. This says root lambda should be of the form n pi, or lambda should be of the form n square pi square for n integer 1, 2 and so on. So, what we have got, our eigenvalues are pi square, 4 pi square, n square, pi square and so on. And what is our eigenfunction? You see C2 sine root lambda. So, corresponding eigenfunctions would be phi 1 as k 1 sine pi x, phi 2 as k 2 sine 2 pi x. So, this C2 I have changed as according to this phi, this lambda 1 and lambda 2, we are writing k 1 and k 2 and so on. Thus, phi n would be k n sine n pi x. Now, we have to choose these k n such that these functions phi n's are normal. That is, now given the weight function r x as 1, we want to choose k n such that 0 to 1 k n sine n pi x whole squared with respect, integral with respect to x should be 1. Now, integrate this left hand side, that is find out this integral. This says is this integral would be k n square 0 to 1 sine square n pi x dx, which we could write as 1 minus cos 2 n pi x, that is sine square n pi x, is written as 1 minus cos 2 n pi x. Now, integrated with respect to x on the range 0 to 1, we do get it to be half k n square. This integral you can do by yourself. Thus, we get that half k n square should be 1, or k n square should be 2, or k n should be square root 2. This value of square root 2, this will give us the normal values or normal function. So, our phi n x should be of the form square root 2 sine n pi x for n is equal to 1, 2, 3 and so on. We already know that they are orthogonal. Now, we have substituted for this k n as a square root 2. So, they are normal as well. So, these phi n x are forming the orthonormal eigenfunctions, or the set of orthonormal eigenfunctions for this given boundary value problem, which is our Strum Liouville problem as well. Now, let us do one more example. Determine the normalized eigenfunction of the problem y double dash plus lambda y is equal to 0, y at 0 is 0 and y dash at 1 plus y at 1 is 0. So, we are getting again this Strum Liouville problem. We had already seen this example and we had found out that the eigenfunction or eigenvalues of this problem are those which are satisfying the equation sine root lambda n plus root lambda n cos root lambda n is equal to 0. Those lambda n's are forming the eigenvalues of this problem. And the corresponding eigenfunctions also we had seen that were of the form k n sine root lambda n x. Now, we have to determine the normalized eigenfunctions, that is, we have to find out this k n such that integral k n square sine square root lambda n x dx is 1. Now, this integrate this integral, it says is k n square half 1 minus cos 2 root lambda n x dx. Which is we can write as k n square into half x minus sine 2 root lambda n x upon 2 root lambda n, that is the integral of this, evaluated from 0 to 1. Now, if I rewrite this one, we are getting k n square by 2 into 2 root lambda n x minus sine 2 root lambda n x upon 2 root lambda n. Now, 2 we are taking common on this one, and when we are putting the value of 1, we are getting is that is k n square by 2 root lambda n minus cos root lambda n sine root lambda n, because sine 2 root lambda n we are writing as 2 cos lambda n and sine lambda n at x is equal to 1, and at 0 because sine is 0 and x at 0 is 0, we are getting 0 there. Now, this thing we can write as k n square by 2 lambda n plus root lambda n cos square root lambda n upon lambda n. Why? Since we do know that the lambda n's are the eigenfunctions which are satisfying this equation, sin root lambda n plus root lambda n cos lambda n is equal to 0. So, substituting sin root lambda n as minus root lambda n cos root lambda n, we do get this one, which says is that we are getting k n square by 2 into 1 plus cos square root lambda n. Now, we want that this has to be equal to 1. This says is my k n square must be equal to 2 upon 1 plus cos square root lambda n and whole square root. So, what would be our normalized eigenfunction? Normalized eigenfunctions are phi n x is equal to root 2 sin square root lambda n times x upon 1 plus cos square of square root lambda n whole square root for n is equal to 1 to 3. They are forming orthonormal set, because we had already shown that these problems are nothing but the Sturm Liouville problems, and they are satisfying this condition, that is A1, A2 is A2 and B2 are not 0. So, they are having that real eigenvalues as well as that eigenfunctions are orthogonal, and here we are choosing these multiplicative constants such that we do get the norm as 1. So, this is also forming our normalized this one. Now, let us see one more result about the zeros of eigenfunctions phi n x of Sturm Liouville problem. What we mean by the zero? Zeros means is that where this phi n x, the function, is 0 for which values of x are, wherever it is crossing the x axis, if I draw the graph of phi n x. This is very interesting result, and this is known as the Sturm comparison theorem. Rather than giving you exactly what is the result, here I would just give you some point or some part of it, that what is Sturm comparison theorem. It says is that whenever lambda 1 is less than lambda 2, then between the zeros of non-trivial solution phi 1 corresponding to lambda 1, there lies a 0 of phi 2, the non-trivial solution corresponding to lambda 2. What we are saying is, we had already find it out that Sturm Liouville problem has real eigenvalues, its eigenfunctions corresponding to the distinct eigenvalues are orthogonal, and they are simple. Now, what we are saying is, one more result we have got, that they can be ordered also. Now, here if I take any two eigenvalues such that lambda 1 is less than lambda 2 and their corresponding eigenfunctions, if we plot, then corresponding to the smaller eigenvalue, the eigenfunction would have zeros, and the zeros of the second eigenfunction would certainly lie between them. Let us have this more nice explanation over here. Let the Sturm Liouville equation be this as usual one, with our boundary conditions a1 y a plus a2 y dash a is equal to 0, b1 y b plus b2 y dash b is equal to 0. And let us have that some lambda 1 and lambda 2 are its two eigenvalues, and let us have corresponding eigenfunctions as phi 1 and phi 2. Then this theorem is saying is, that is phi 1 is the eigenfunction corresponding to the smaller eigenvalue, and phi 2 is the eigenfunction corresponding to the larger eigenvalue. Then you see that graph, what it is saying is, it is simply telling us, you see this lighter line, this is corresponding to the larger this is smaller eigenvalue. We are having the 0 over here, 0 over here, 0 over here, and we see this another colored line, this is for the graph of phi 2, that is corresponding to the larger eigenvalue. You see its 0 is here, that is between the zeros of these two. Similarly, of course, the another 0 we are matching here. Here again we are getting the zeros of these function are these two, and in between them there is a 0 of this function. That says is basically as we are increasing our eigenvalues, because they can be ordered, corresponding eigenfunctions are giving us the zeros more nearly, or we could get more kind of this kind of structure. Let us see with the help of one example of for this one also. Let our Sturm Liouville problem as first one we have already discussed, y double dash plus lambda y is equal to 0, y at 0 is 0 and y at 1 is 0. Then we do know that general solution of this we had already done as C1 cos root lambda x plus C2 sin root lambda x, lambda is greater than 0, because for this we do know that for lambda positive only this has eigenvalues, and corresponding boundary conditions had given us non-trivial solution phi lambda not 0 as, you see, you do remember this, just now we have done C2 sin root lambda is equal to 0, or we do require sin root lambda is equal to 0. This says root lambda should be of the form plus minus n pi, this is the eigenvalue, or lambda is n square pi square for n is equal to 1, 2 and so on. So, eigenvalues of the given boundary value problems are n square pi square corresponding, that is pi square, 2 square, pi square or 4 pi square and so on, and let us take, we see that is how we had ordered them. Pi square is certainly smaller than 4 pi square, is certainly smaller than 9 pi square and so on. So, we can order them. Corresponding eigenfunctions k n sin root lambda n x, just now we had find it out. Now, let us take root lambda n should be n pi. So, k n sin n pi x. Let us take the first two eigenvalues lambda 1 and lambda 2, and the first two corresponding eigenfunctions k 1 sin pi x and k 2 sin 2 pi x. Now, let us see the zeros of these two functions in the graph. This is the graph of sin pi x, this is the graph of sin 2 pi x. Now, again you are seeing is sin pi x means is, that is I would be having the at x is equal to 0, at x is equal to 1, at x is equal to 2, that is sin n pi is 0. Similarly, for sin 2 pi x we do know certainly that it should be n is equal to 0, n is equal to half, n is equal to 1, n is equal to 3 by 2, because it is 2n. So, 2n is integer, or rather we do get all those half values also we would be getting zeros. So, we would be getting, of course, some points we are matching the zeros, but certainly between the two zeros we are getting this one. Basically, this result is saying is that as we are getting more higher eigenvalues, our corresponding eigenfunctions will become more dense, or the zeros would be more near on the real line, we would have more alterations. This is all we do have for our Sturm Liouville boundary value problems. So, today we had learned the properties of Sturm Liouville boundary value problem. The last lecture we had learned boundary value problems. So, basically these two lectures are forming one unit for the boundary value problems, or more specifically we have done Sturm Liouville boundary value problems. For this we had learned that they are not as simple as the initial value problems. We are not guaranteeing that is when they are going to have the solutions. So, we had generated from there, that is they are having eigenvalues and eigenfunctions, or rather when they are having a solution, non-trivial solution, we call them eigenvalues and eigenfunctions. So, first we tried to find out the eigenvalues, corresponding eigenfunctions, those are the solutions of the boundary value problems, and for this we have done the special kind of equations, those we called Sturm Liouville equations, and there we had used the simple linear boundary values, and we called incomplete Sturm Liouville boundary value problems. We have learned certain properties of these problems. They are remaining in the real line, that is all the solutions are existing on the real numbers itself. That is all for this one. Thank you.